Okay, so good afternoon. We'll continue with the lecture. We were here, if you can recall, we were finding the conjugate of the following functions. Okay, so if you recall what was the conjugate, so for a function fx, the conjugate is defined as fy. Okay, so let us say it's some other function f star, and this is the supremum over x of y transpose x minus fx. Okay, so this is the conjugate here. Okay, so f star is the conjugate of f. Okay, so this is something we did in the last class, and we want to continue from there. And we have found conjugates for this in the last class. And today we would like to find conjugate for exponential, negative entropy, inverse, and so on. Okay, so let us see the exponential case. So this is done already in the last class. So you see that video. So this is also done, log x. Now we want to do exponential of x. Okay, so what is the conjugate of e to the x, right? So to find the conjugate, we have to write down the f star y. So f star y is supremum over x, and then y transpose x minus fx. Okay, so this is supremum over x. Since this is a function from real to real, so y is just a real number, so y transpose is just y. So this is like yx minus, and fx is e to the x. So this is what we are supposed to find. Okay, supremum, this is what we are supposed to find. So and since f star has to be a valid function, we have to avoid those values for which this becomes unbounded. Okay, so we have to find, for f star to be a valid function, we have to allow only those y for which this supremum value is not unbounded. Okay, so it's within limits, within not minus infinity, not infinity and minus infinity, right? Okay, so this is the only thing we have. So what we have to focus on is whether this guy y transpose, yeah, so whether this guy yx minus ex is bounded, and for which values it's bounded, and so on. Okay, exponential is defined over all of R. So the x domain we are clear. Okay, so domain of f is all of R. Now we want to find a valid domain of y, and valid domain of y comes from whether it remains bounded or unbounded on certain values of y and x, right? So that we have to figure out. So the way we plan to do this is like usually we fix some y, okay, and then we see for those cases of y whether it remains bounded or not, right? So usually the cases we consider are usually, but not always the same. Like usually the cases we consider are, we do part by part. So y greater than 0, does it remain bounded? And then next case could be y less than 0, does it remain bounded? And then another case could be y equal to 0. Okay, so usually we try to partition y in this way, and case by case we try to do. Like it's very rare that for all y this will happen. If it so happens that it's true for all y, then obviously domain of f star will become all of R, but that is not always the case. So we will go case by case basis, just like we did it in the previous cases. So let us say for y greater than 0. So y greater than 0, what can we say about this, right? So y is greater than 0, so yx minus e to the x. Okay, or okay, let me do the y less than 0 case first, and then I will come back to y. Okay, first let us do y greater than 0, y less than 0 case, right? So if y is less than 0, what can you say about this? Like whether it will remain bounded or unbounded. Okay, so I can for convenience I can define this as g of x. Okay, so I define g of x is equal to yx minus e to the x. Okay, and now we are talking about, so y is something fixed but less than 0. Okay, something fixed but less than 0, and what we have to vary is the x, because that's where we are computing the supremum. So for a fixed y less than 0, okay, can we guarantee that gx is a bounded function, right? So that's what we are talking about here. So for all x, right? So for all x, we have to guarantee this, right? Okay. So what do we know about this? So for finite y and finite x, this is going to be a finite number anyway, right? So there is no issue when y and x are finite. So the cases that we are left with are y less than 0 and x tending to infinity, and y less than 0 again, but x tending to minus infinity. So these are the cases, asymptotic cases, where it may go unbounded, because from this expression we know clearly that for any fixed y and x, it is bounded. Okay, so unboundedness might come only when x and y are going in limit towards infinity, right? So those are the cases we have to explore. So y less than 0, and yeah, so is this like unbounded? Okay, so y less than 0, so what will happen is, if x is like going to infinity, right? So if x is going to infinity, like this will go where, right? So y is less than 0, so this whole term will be less than 0, right? But then x is tending to, let us say, infinity.
Sir, your
Sir,
audio
I
got.
think you're on mute. Sir, you are not audible. Excuse me, sir. Hello. Hello, sir.
No, sir, we can't hear you.
Hello.
Yes,
We
sir.
can hear
Now
you
you're
now.
audible.
Yes, sir, audible.
Okay. So let us continue with then. Okay, so I think since beginning you are not able to hear, right?
No, you
No,
were
sir, at
audible
info
earlier,
minus
but
X,
Okay.
it suddenly dropped.
So yeah, so I will repeat this part very quickly. Okay. So yeah, so we are supposed to find conjugate of this function fx is e to the x, and this we know is a function well defined from real number to real number. In other words, it can take any value and it's fine. And then
we again lost you, sir.
hello.
Yes, sir, we can hear.
You can hear, right? Okay. Okay, so we'll continue. So we have to find the conjugate of this, and this will be yx minus e to the x. And for y less than 0, we want to see whether it goes unbounded, right? So as x tends to infinity, because y less than 0, so yx will tend to minus infinity. And minus of e to the x will also tend to minus infinity. Okay, so this whole term is going unbounded. Okay, so its whole term is going unbounded, and as x tends to minus infinity, as x tends to minus infinity, what about this guy? Yx is tending to positive infinity. Okay, although this guy is going to 0. Okay, so minus e to the x is indeed going to 0, but overall gx is going to infinity. Okay, so it is like unbounded, and for supremum this is the case that we worry about. Okay, this is the case that we worry about, where it's going to plus infinity, and this is where this is not going to be defined. Okay, so we know that for y less than 0, this supremum is, there are values of x for which the supremum is going to infinity, and this supremum will catch the higher values, which will be like plus infinity, right? So this is going to be unbounded. Okay, so this is not going to be well defined. So for y less than 0, f star y is not defined. Okay, so this we know. Okay, so now we consider the case where y is greater than 0. Okay, so if y is greater than 0, then what do we have, right? So for y greater than 0, what do we have? So I think what I will do is, like, I will use the space from here. Okay, so for y greater than 0, Okay, so for y greater than 0, x, y minus e to the x, like what do we know about this, right? Does it like for a finite y and x, this is bounded, that is clear. Okay, so now we have to check the asymptotic case. So asymptotic case, y greater than 0 but something fixed, and x tending to positive infinity and negative infinity. These are the cases where it may go unbounded, right? So y is greater than 0, right? And x is going to, let us say, infinity, right? So what can we say about this case? So this is like this term is going to infinity. Okay, and this term is also going to infinity. But there is a negative of that. So we are not sure right now. Okay, because there is a negative here, right? So we cannot conclusively say here in this case that overall it's going to infinity, right? Because something going to infinity minus something going to infinity may not go to infinity, right? Overall. So that's where that's where we are not very sure. Okay, and x tending to minus infinity. So this is like x tending to infinity and x tending to minus infinity. So this is yeah. So this term will go to so x y. Since y is greater than 0 and x tending to minus infinity, overall it's minus infinity, and minus e to the x tending to minus infinity will go to 0. So overall it's going to like xy minus e to the x. Here we are certain that overall it's going to minus infinity. But since we are dealing with supremum, this case doesn't bother us. What bothers us is this case, okay? Because this minus infinity won't be caught by the supremum anyway, because supremum is tracking the higher values, right? So supremum would be interested in these values, like where is there a bound above? Okay, so this case we are not sure about. So our preliminary analysis doesn't say anything. So we would go with the view that maybe it's bounded, and if it is like bounded, then it may have supremum, because if a function is bounded, then it must take that value, right? Because so let us see for that, right? So the question is like, can we find a maxima of this? Like, what is the maximum value of this? What is maximum or supremum, whatever, right? So as e to the x, okay? So what is the max of this, right? So for that we use the calculus thing. So for us this is like g of x, right? We treat this as a function of x. So g of x, so g prime of x of this, right, as a variable of x, right? So this is like y and minus e to the x. Okay, so derivative of e to the x is e to the x only. Okay, and we equate this to 0 to find the critical points. So this implies y is e to the x. Okay, so this implies x, because we are solving it for x, right? So x, we take a log, right? So log, so x will be log y, the natural log. So this seems to be a point on the critical point. Now we are not sure whether the critical point could be maxima or minima both. So we need to take the double derivative to do further test of identifying whether it's maxima or minima. So if we do double derivative, then, and this is with respect to x. So this guy becomes 0, right? So this is like minus e to the x. Now exponential is always a positive function. So negative of the exponential is always a negative function, right? And in particular for x is equal to log y. Okay, I mean it is true for all x, but including this case. So this means that this is going to be a maxima. Okay, because double derivative is negative. So this means that the point x equals to log y is a maximum. Implies x equals to log y is a maxima. Okay, there can be many maxima because it may not be a convex. So this is like a maxima, right? So in this case, we have found the supremum, which is happening for x equals to log y. Okay, so supremum is found. Okay, for all y greater than 0, the x for which the supremum is achieved is log of that log of y of that y. Okay, so in this case now we can now finally write down the f star y. So f star y, which was like the supremum of this guy. So supremum of this is achieved when x is log y. So wherever there is x, we will put log y. Okay, so this is like a log y and then times y, and then minus e to the log y is just y. Okay, so this is like minus y. So this is the conjugate of e to the x. Okay, so this is the conjugate of e to the x. So as you can see, it's not that difficult to find a conjugate. Let us do one more. I think I have two more, but let us try to do one more example. This is called entropy. Okay, so entropy function. So let us try to find a conjugate for this. First of all, what are the valid values of x? So what are the valid values of x? Well, log is not defined for negative values. It's only defined for positive values of x, and x is defined for all. So overall, this is defined from r plus plus. So plus plus, remember, it was the strictly positive thing, and this, yeah, so it's defined for this, and otherwise this guy can take I believe all real values it can take. Okay, because negative is possible. Okay, so this is, I mean, we don't care anyway about this. What we worry about is the domain of f. So domain of f is r plus plus, because when we are computing conjugate, we can take supremum only over the valid domain of f, which is r plus plus in this case. So first thing is to identify valid domain of f. Now we have to do like as usual, the case by case basis of what are the possible values of y and so on, right? So in this case, so what do we have? At 0, this is 0, right? And so what we are looking at, again, let us write down the conjugate. So this is like a supremum of over x of y transpose x. So y transpose is just y here. So yx minus x log x. Okay, so this is what we are supposed to solve. And so what are the cases we have, right? So is it like bounded above on r plus? Okay, that's what we are trying to say. Is it bounded above r plus for all y, right? So is it like, I mean, here again we are tempted to say whether we should check for y greater than 0, y less than 0, y equal to 0, and so on. Yeah. So what do we think about this, right? So is this like a bounded function for all y, right? So let us try to do the analysis for this. So the function that we have is g of x is yx minus x log x, right? So so y positive, let us say, right? So y positive and x is always positive, like that is guaranteed from our domain of f. So y is positive, x is positive. Can't really conclude right now, because this is like something like for fixed values of x, these are finite numbers, so no worry about finite values of x and y. Gx is finite, no problem. Now we have to take the asymptotic cases, right? So y greater than 0, let us fix this. And as x tends to infinity, positive infinity, so this guy like yx is tending to positive infinity, and x log x, we know both are increasing functions, so they also tend to positive infinity. So it's like infinity minus infinity. So these are the cases where we cannot conclusively say that the whole term is actually going to infinity. Actually, it will depend on the dominating term, right? So which one is a more dominating term? So these are the cases where we have to to pause and like go ahead and like see critical points. Like maybe there is a bound. Okay, so in that case we will go ahead and find the critical point in the hope that there is some maxima achieved somewhere. Okay, so the critical point will reveal that. So let us go ahead and do that. So this is like gx. So what is g prime x? Remember, it's a function as a function of x. So as a function of x, so y is a constant, so y will remain. Okay, y plus and yeah, so and this is like x log x, right? So this is not really plus here. This is like minus. Yeah, so this is like minus. So we have to take the derivative with respect to this. So x, right? So this is like first function into differentiation of the second plus second into differentiation of the first, right? So this is y minus 1 minus log x, right? So this is the function we have. So this is like, okay, so from here we can find the critical point, right? So g prime x equals to 0. Okay, so this implies what? Y minus 1 is equal to log x. So if we solve for this x, then it will be e to the y minus 1. Okay. Okay, so we have found a critical point, but we are not sure whether it's a maxima or a minima. So we will go ahead and do g double prime of x and see. So this guy being a constant, this will vanish, right? And this is like minus of 1 over x. But x is positive, right? So x is always positive. That is restricted by the domain of f itself. And so this whole thing is positive, and then we have a negative here. So overall it's negative. Okay, so g prime is negative, and in particular this should be negative also for this value, which is y minus 1. So we conclude that x equals to this is a, so this implies that x equals to y minus 1 is a maxima. Okay, in other words, this is the maximum value that the function is going to take. Okay, so so we have solved the supremum problem, right? So this supremum is achieved for e to the y minus 1. Okay, so for x equals to e to the y minus 1. So in this case, again, we can write this implies f star y is yeah, so f star y. So wherever there is a x, we will put e to the y minus 1. Okay, so this is like y y times e to the y minus 1 minus, yeah, it's okay. So y, and then yeah, so again, like x is e to the y minus 1 times, and then log x is y minus 1, right? Yeah, log x is y minus 1. So it seems like something will simplify, right? So overall it will be minus, because y e to the y minus 1 will get cancelled. Okay, so this gets cancelled with this. Okay, so what is left is positive of e to the y minus 1. Okay, that's it. That is like f star y. Okay, so for the conjugate, like I think I will stop here. I think I have given you enough thing, so you can solve some of these in the upcoming assignment, and I can continue. Okay, and let me check if everything is okay.
Hello, sir.
Yeah, I'm audible. Okay, yeah, yes.
So suppose we are not able to find a maximum, then we cannot find a conjugate function.
Yeah, if there is no maxima, then it immediately tells you that it's going to be unbounded anyway, right?
Yeah.
Not being able to find maxima is a guarantee that there must be unboundedness here. Okay, so for those y values, you should immediately discard. Yeah.
Okay.
Okay. So let us stop here. And there is one more example, and this example goes with in a similar spirit like we did in the other cases. So you can do this case by case analysis, and you should be able to solve this. Okay. Now what I will do, so this will be the conclusion of the convex function chapter. This is chapter 2 of the Boyd book. Okay. So I am following Boyd book very closely. Okay. In case you are wondering what is the textbook, then this is the Boyd's convex optimization. This is a very fat book, and you will see that I will cover almost all the book, and apart from this, we will do a lot more. Okay. So, but not going in the special cases of the book. Okay, so I will skip some of the special cases, those that are not needed in the first course. So, okay, so we are done with the chapter 2 of that. And you may think that we are going slow, but once we hit the algorithms, we go very quickly to all the chapters. Okay, so we have concluded so far is what is a convex function. So they are like typically like ball shaped, and concave is like this way, and neither concave nor convex will look like this, and both convex and concave will be like this. Okay, the flat thing. Okay, so like the constant functions are like both convex and concave, not just constant, but also like linear functions. Okay, so I hope this this happens to be like the solid background that you need. Okay, if you want to do research in optimization. So that part is done, and now we will move into the actual maximization and minimization problem. What are the variants? How do we classify these, and so on? Okay, so now we actually get into the problem formulations. Okay, but we have to introduce the standard terminology for this. Okay, so when someone gives me a problem, how can I put this in a certain form? From here onwards, I may actually be able to use the library or something like that. Okay, so we have to understand the form. So a general optimization problem will look like this: a general optimization problem. Okay, not necessarily convex. Okay, so I will not define this as a convex optimization problem. I will just define this as optimization problem. I will come to convex optimization problem later on. Okay, that will require the objective to be convex, and inequality Fi, Hi all should be convex, domain should be convex, and so on. Okay, but right now we are not talking about convex. We are talking about any general optimization problem. Okay, any general optimization problem looks like this. So you have some objective function which is f naught x. You have inequality constraint because of this inequality, and you have equality constraint because of this. You can have m number of inequality constraint. You may have p number of equality constraints. Okay. So now I'm going to just write down those things. Okay. And so the problem is find an x that minimizes the objective f naught x among all x that satisfies the inequality constraint and that satisfies the equality constraint. Okay, so this is the optimization problem. Okay, now x is called the optimization variable here. Okay, so this x is called the optimization variable. Okay, these are the things you have to memorize. Okay, because we will be using this language in future. F naught, as I said, is called the objective function. Okay, or the cost function or loss function, depending on where you are trying to use optimization. Okay, so if you are in the industrial setting, then you have cost of transportation, whatever. Okay, so manufacturing cost and so on, and you want to reduce the cost and so on. Or you can also formulate it in another way, like profit function, right? So then you may want to maximize the profit, minimize the cost, and so it depends. Loss function is typically used in data sciences where you have certain loss function defined and you want to minimize the loss of your model on the trained data. Okay, so that's where you are like learning the parameter and so on. So depending on the problem and the domain you are working with, you will be talking about cost function, loss function, profit function, and so on. But in general, technically we call this objective function. Okay, and it could be about maximization, it could be about minimizations. These inequalities are called inequality constraints. Okay, so these are the constraints your problem has to satisfy. Okay, so you have to minimize this given that it also that x also satisfies this and this. Okay, so these are like the constraint on your variable x. And fi are called inequality constraint functions. So they themselves are called inequality constraint functions. Okay, so here I is not equal to 0. Okay, because for I equal to 0, this is the case we have, and that is called objective function. For I greater than equal to 1, these are called constraint functions. And similarly, now you can guess h, I, x are called equality constraint functions. Okay, equality constraint functions. Okay, so here I have to write functions. So yeah, so someone so I may talk about, okay, so f naught is like objective function, the fix are my constraint functions, inequality constraints, and hix are my equality constraint functions, and so on. Okay, so today you will see that we are just defining so many terms. Okay, so these equations are like equality constraints, and then the hi themselves are called equality constraint functions. Okay, so now let us see if there are no constraints. In other words, m is 0, p is 0. Okay, so this will mean that there are no constraints at all. No equality constraint, no inequality constraint. Then we call that problem unconstrained problem. Okay, then we call unconstrained problem. Okay, the domain of our optimization problem will be the intersection of the domains of all these functions: objective function, inequality constraint function, and equality constraint function. Okay, and that will serve as the domain. Okay, so this fi for I equals to 0, it includes the objective. So you have to take intersection of all the domains, and that will be the valid domain over which you can talk about minimizing. Okay, so that's like the natural thing. A point x is called feasible if it satisfies the constraints. Okay, so a point is feasible if it satisfies both the inequality constraint and the equality constraint. Okay, so I will also have some examples to practice this, but for the moment memorize these things. Okay, the optimization problem is called feasible if there exists at least one feasible point. Okay, in other words, the feasible set, the set of all x for which these inequality and equality constraints should it satisfied, must be non-empty. Okay, there must be some x for which these inequalities are satisfied, and then we call the optimization problem to be a feasible problem. Okay, it may happen that someone told you to minimize, but you know that these guys are contradictory, like they cannot hold together. In that case, you will return the problem to the person and say that, well, this problem itself is not feasible. It's not a well-found problem. So go ahead and check again your equality and inequality constraint, right? So first step for you to solve would be to check whether the inequality constraints are actually satisfiable or not. Okay, now feasible set or constraint set. So these are set of all feasible points. Set of all feasible points, you put it in a set, and that will be called feasible set or constraint set. Okay, the next important thing is optimal value. Okay, this is what we are looking for. So the optimal value p star is defined as the infimum of the objective function f naught x. Okay, f naught x is the objective function, and obviously it should satisfy, along with that, it should satisfy the inequality constraint and the equality constraint. So this p star is the minimum value that your objective function takes, along with satisfying the equality and inequality constraint. Okay, so that is called the optimal value. Okay, so the optimal value does not have to be the minimum. Okay, so optimal, if your problem was maximized, then optimal value would have been the supremum. Okay, so the optimal value could be the minimum value or the maximum, or to be more precise, supremum or infimum. Okay, so these are the keywords that you should memorize. Now p star is allowed to take extended value. In fact, by using infinity, it's infimum, we are allowing it to take positive infinity also or negative infinity also. Okay, so it is extended to take plus infinity or minus infinity. Of course, in that case, we will say that it's a unbounded and so on. Okay, but mathematically we allow positive infinity, negative infinity values as optimal value. Okay, although it may not make sense because infinity value no one cares about, right? Unless like one has to see like profit is going to infinity and so on, right? But in reality we don't see that, right? Okay. Infeasible problem is a problem where the optimal value, and remember that all this thing that I'm talking about is in the context of minimize, okay? Because maximize problem can be changed to minimize by doing minus of f naught, okay? Don't have to change anything with the constraint. Constraint never have to change, but only thing I have to change is the objective, and maximize becomes minimize, and so that's why we will always talk about minimize. So all this thing that I'm talking about is in the context of minimize, okay? Okay. I hope you can hear me because I heard some sound once again. Okay, if you don't hear, then immediately tell me, okay? Okay. Sometimes my yeah, you can hear me.
Sir, in the P star, the x belongs to the feasible set, right?
Yeah, X belongs to feasible set because because these are being because I'm already asking for the simultaneous things to get satisfied, right? If there is no such X, then I will get into infeasible problem, right? Anyway. So in that case, I will. So if the problem is infeasible, then this is the second point that is taking care of that, because the infimum of an empty set, right? So infeasible implies this set. So this set is empty, right? Infeasible means that there was not a single X that could satisfy this. So this will mean that this set is empty, and this set is empty, and we are doing infimum of the empty set, and infimum of the empty set by definition is okay? So by definition is said to be plus infinity. Okay, infimum of empty set is plus infinity, and the supremum of, and this is like by definition, okay? You should not think too much about this. And this is like minus infinity, okay? So this is another way to say it. So if P star is going to infinity, so it means like, okay, maybe this set became infinity. I mean, not maybe, but this set indeed became empty, because in that case only we got infimum to be infinity. Okay, because for any other case infimum won't be like that, right? Okay. So this is another way of saying that the problem is infeasible, okay, when the optimal value we get is like infinity. Okay, so which directly implies that the set was empty. Okay, the feasible set was empty. Okay, so these are like the things that we recall. I mean, we remember. Okay, we use the fact that infimum phi is infinity. That's what I said. And a problem is said to be unbounded below if there exists some sequence xk. So there exists, so this is notation for the exist, some xk sequence. Okay, as so x1, x2, x3, so on. You can produce a sequence such that f naught x, your objective is going to minus infinity as k is tending to infinity. Okay, so as k is tending to infinity, your objective is tending to minus infinity. Then I say that the problem is unbounded below. Okay, so that makes sense. So the problem for certain sequence of x, as it's approaching infinity, it's going to minus infinity, is unbounded below. And okay, now I can talk about optimal point. Remember, there is a difference between optimal value. Optimal value is the actual value taken by the function. Optimal point is the point x star for which the optimal value is achieved. Okay, so that's the another point. So this is called optimal if it solves the given optimized problem. In other words, it finds the minimum of this. In other words, finds the optimal value of this. Okay, so and additionally, obviously, x star has to be a feasible point. Okay, like for a definition, we want x star to be feasible. Like we don't want any x that does not satisfy and then it achieves the minimum. Okay, that's not the objective here. X star will be declared to be optimal. First of all, it has to be a feasible point. So it has to satisfy these inequality constraints and so on. And for that X star, the optimal value is achieved. Okay, so P star is the optimal value is achieved. Okay, so that's the definition of optimal point. Optimal set, the set of all optimal points, okay, is called an optimal set. So it may happen that like I may have many optimal points. The function is achieving minima at many points, not just one unique point, right? In that case, I can collect all those points and put it in an optimal set, because sometimes it may happen that the function is having the same minimum value on whole set of points on a line. Okay, so it may happen, the cases might like that happen. So in that case, the optimal set will be that line. So set of all optimal points is called optimal set. If there exists an optimal point, then we say that optimal value is achieved and the problem is solvable. Okay, so if there exists some point in the optimal set, at least one point we want in the optimal set, then for that the optimal value is achieved and the problem is called solvable. If my optimal set is empty, not even a single point is there, then it means that I have not got any optimal point. In other words, there was no feasible point for which the optimal value could be achieved. Okay, so and then the problem is like unsolvable. If the optimal set is empty, then we say that the optimal value is not attained, obviously. So if the optimal set is empty, then there does not exist any X star, okay, for which the P star can be obtained. Okay, so we say that the optimal value is also not attained. If X star is not there, then P star also not be there, right? Okay. Okay, now what I will define is something called locally optimal points. Okay, locally optimal points. So so the problem, all this is exactly the same. So we call something called epsilon suboptimal point. Okay, so X bar is called a epsilon suboptimal point if fx bar is less than or equal to P star plus epsilon. So I know that optimal value is P star, and if I can find an X bar which is just epsilon distance from the P bar, okay, so which is like just epsilon distance from P bar, or like within epsilon distance from the P bar, right? I mean P star. So this is like P star, and remember we are in a minimization problem. Okay, so I am always going to P star like this because it's a minimization problem, right? So at worst I will stop somewhere here, right? So because let us say I'm using some iterative method and so on, gradient descent, whatever. So I get x1, then I get x2, then I get x3, and I'm approaching here, right? So obviously I'm expecting that iteratively I may get close enough. So let us say somewhere here, which is like P star plus epsilon. Okay, so this distance is like epsilon. Okay, so then if I'm somewhere here, like within this value, in other words, like my objective, so it should be 0 here. Okay, so my objective is like f naught x bar is somewhere here. Okay, so f naught x bar is somewhere here, f naught x bar. Then I call it within epsilon range. I am within the epsilon range of the optimal value. Okay, so in that case, I will call the corresponding x bar epsilon optimal. Okay, so it's not optimal yet because I did not hit the P star yet, but I am within the epsilon range of getting to the P star. Okay, so that's the, so we can call it like some locally optimal point. Like it's like locally, like I'm like close. Okay, locally optimal, but not really like not really actual optimal, right? Okay, so that's called epsilon optimal, and this will play a major role because what will happen in practice is we will always, not always, but most of the time, like in many realistic scenario, you don't hit the optimal value you don't hit the optimal value at all. Okay, you have to like go by iterative method. Like I have told you about gradient descent method. That's a iterative method. You produce x1, x2, x3, so on, and you are moving closer to the optimal value. Okay, or the optimal point. So so you will stop at some point. Okay, because your algorithm may not go exactly to the optimal value. Okay, so you have to decide at some point that okay, I'm okay with this epsilon threshold or something. Okay, well the problem is like, and the problem is that like you you may have to know also implicitly what is p star, right? I mean, how will you know epsilon, right? So this will look very paradoxical right now for you, right? How do I like how do I guarantee when I stop, right? Because I already don't know p star. So if I don't know p star, then how will I know that my solution is epsilon distance from p star? In other words, how will I know that I have found some x bar which is epsilon distance from p star, because I don't know p star anyway, right? So this will look a little bit paradoxical right now, like how, but we will see. Okay, there are ways to find some bound and so on. I mean, a simplest case would be like, let us say if you are doing some neural network thing or something like this, you define some loss function, okay, and then you have, let us say, a neural network model, okay, and then you have x, and then you have the actual level that you are given, okay, and your loss is defined in some valid measure. Okay, so let us say a very simple would be like, let us say I want to do like L1, L2 norm and so on. Okay, so in this case, I am already aware of the lower bound. Okay, so lower bound of a norm is like greater than equal to 0. So norms are always greater than equal to 0, right? So in this case, what you may assume very well is that ideally what you would have is a p star is like 0. Okay, I'm not saying that it has to be, because it still depends on these guys, right? But assuming that like your neural network is powerful enough, bigger enough, okay, such that it will get exactly equal to the level, okay, provided the weights are well tuned. I mean, to well tune the weight, you have to actually run this gradient backprop and so on, and all those things. We will see these things later. But for the moment, let us say this is how your objective function is defined, f naught x, and let us say it's unconstrained problem. Then you more or less have a idea that your optimal value is supposed to be 0. So in that case, like if your f naught xk, where xk is produced by the gradient descent, if this is reading close to like 0, okay, then you are happy. And then let us say your loss became let us say -9. Okay, let us say your loss became 10 to the -9. Then more or less you are 10 to the -9 optimal. Okay, suboptimal. You can think like that because you have a fair idea that your loss, which is p star, is 0. Then you can rely on this function value, objective value, and you can keep printing during iteration and say, okay, I'm very close. Now I can stop. So you can say that, okay, your epsilon will look like this, okay, which is the objective function value itself. Okay, so we do get some fair idea of that, but the problem is like I mean, getting a sense of the minimum value is not really I mean, it is a big deal, but it's not really the most important thing in some problems. What is the most important thing in some problem is for which values of x. Okay, I mean, to be more precise, it should be like some theta. Okay, where theta is like some parameter in my model. Okay, so I'm tuning a parameter of my model. So I'm minimizing this loss. Ideally, I know that it should go to 0. Okay, and then I will keep doing the iteration, and then I will at some point I will stop and say, okay, I'm still happy with -9. I think my model has trained well, and then I can stop with this these parameter theta that I obtained. Okay, so instead of xk, you can say it's like theta k. So so in many problems, what is really the most important is for which values. So in other words, what we are most worried about is the optimal point. Okay, optimal point becomes very important. So in neural networks, in machine learning, deep learning, the optimal points for you are the parameters of your model. Okay, what is the best parameter of my model? Okay, for which my loss is minimized. Okay, so there you worry about optimal point, not value. Okay, value is more or less, you know, okay, ideally it should be 0, right? Okay, so that's what I said. An epsilon optimal set will be the set of all possible epsilon suboptimal points. So if you think of like a higher dimension, let us say, okay, so my P star is sitting somewhere here, okay, and let us say I'm solving my problem in like using like let us say some R2, okay. So then I can approach this via many ways, right? So my one, let us say, gradient descent method, one type of gradient descent method may lead it to like this. Another type of gradient method is approaching via this. In fact, this will be the case because remember in gradient descent we don't know the starting point, right? So one possible sequence could start from here. So your x naught may be here, the initial guess, and x naught could be here, x naught could be here, because usually it's like you start from random value, right? So there are many possibilities where you can stop near this, and this whole set of points. Let us say these are within epsilon distance. So all these points will form this epsilon suboptimal points. So all these points are within epsilon distance from the P star. Okay, so this is called epsilon suboptimal test. Okay, I mean set. Okay. Okay, what is active constraint? So if x is feasible and Fix is equal to 0 for that x, then the ith inequality is called active. Okay, so this active inactive will come a bit later, but for the moment you memorize. Okay, so I'm not going to say too much about active inactive very recently, maybe after one class, but right now let us just remember this. Okay, so if x is feasible and Fix is exactly equal, because remember in inequality we have both possibilities, less than as well as it could be equal for some x. Okay, so it may happen that there is some x for which some inequality is equality actually, and some equality others are equality anyway, right? So some inequality may become active for certain feasible x, and we call it active when it hits the equality. Okay, it hits the equality, then we call that x to be feasible. There is a geometrical interpretation for this active inactive. I will do that a bit later. Okay. Okay, so but for the moment we memorize this. Okay. Inactive constraint is when it is strictly less than 0. Okay, so if x is feasible, and then we call the ith constraint inactive constraint if for that x Fix is strictly less than 0. Okay, strictly negative, then we call it inactive constraint. Okay, then there is redundant constraint. Redundant constraint is a constraint if we remove this, it doesn't change the feasible set. So basically it does not have any impact on the minimization problem. So there could be some constraint which are absurd, not absurd, I mean absurd will lead to infeasible, but constraint that is included in some other constraint. Okay, so then you can eliminate some redundant constraint and it's not changing the feasible set at all. Okay. Okay, so feasible set we have already, like in words we have described. So these are set of all x that satisfies the inequality constraint and the equality constraint. Okay, so that's the feasible set. So more compactly, if we recall, then we can also write minimization problem like this in a short form. So this is our objective function, and constraint can be put in some 1 omega. So I can hide all this constraint in omega, hide all in a set. Okay, so I can hide all this in a nice set, and that takes care of this, satisfying all this, and then I can write in a very compact form such that x belongs to omega. So x belongs to omega means that x must satisfy the inequality constraint and the equality constraint. Okay, so this is a very short form, and minimize can be written like min, and subject to can be written as s dot t. Okay, f is objective and x is called decision variable also sometimes. Okay, so this is the short form notation of optimization problem. Now let us see some examples. Okay, so minimize f naught x is 1 over x. So this is the plot of 1 over x. Okay, and subject to x belongs to R. Okay, so this is the constraint that you have. In other words, if I write in terms of inequality, then this is like, okay, I mean, this is like all of R, right? Yeah, this is all of R. When I'm saying R, then it's like unconstrained problem actually in this case, because it's all of R, right? Unconstrained problems are when x belonging to all of R, R2, all of Rn, something like that. Okay. Okay, so let us answer these questions here. What is the feasible set here? Okay, so what is the feasible set? So feasible set. Okay, I think I have. Yeah, I think I have not read this completely right. Here I'm defining f not to be going from R plus plus. So R plus plus, remember R plus plus is the positive number, strictly positive to R. Okay, so this is the domain that is well defined here. Okay, so now what should be the so naturally you see when a domain is like this. Okay, so your x is now already restricted to positive R, right? Although here I have said this, but now it's like you have to take the intersection, right? So you are now restricted to now positive R only, positive values only. Okay, so the feasible set in this case will be set of all positive, strictly positive numbers. Okay, and what is like p star, right? What is p star? So what could be the optimal value of this? Okay, so can you tell what is optimal value?
0.
0. Okay. So is the optimal value achieved? So p star is 0. Now the next question is the optimal value achieved? What do you think?
No, I don't
No.
think it should. It's like asymptotically 0.
Yeah. So it is achieved only at infinity, but infinity is not there,
So epsilon optimal.
right? Yeah, infinity is not a real number. Okay, remember that infinity is not a real number. So it is not achieved actually. P star happens only at infinity, but x equal to infinity is not allowed. So this is like no. Okay. So now let us look into this next question, just to practice a little bit about what we have learned. So minimize f naught x, which is minus log x. Okay, subject to x belongs to R, and the domain of f objective function f naught is R plus plus to R. So again, it's like strictly positive real numbers are the domain. Now the question is, what is feasible set here? Okay, what is feasible set, and what is p star? Is the optimal value achieved? And is this problem bounded below? So these are the questions we want to answer, right? So feasible set, right? So first of all, we have to look into the domain. What are the x actually allowed? Although this is saying unconstrained, but then when I look at the domain, I immediately figure out that it is only allowing strictly positive. So that's where my domain gets restricted now. So strictly positive numbers now serve as a feasible set because there is nothing else here. Okay, so feasible set is like R plus plus. So that is done. So, and what is P star in this case? What is the optimal value in this case? So what do you think? Optimal value? This is monotonically decreasing, right? So this seems to be like the previous case only. Monotonically decreasing, and it is going to 0 only because log x goes to infinity. So minus of log x. Oh, 1 second.
So it won't be 0, right? It will be less than 0 because at point x equal to 1, it gets 0.
Yeah. So it's like less than 0, right? Okay, sorry. Yeah. So what is P star then in this case? Is it like always decreasing? Like, is it going to minus infinity, or it will like settle at some point?
So maybe it is log of minus x.
No. The question I think is correct. Log of x, and it's minus of log x.
It should go to infinity then P star.
P star should go to positive infinity or negative infinity?
Negative, sorry, negative infinity.
Negative infinity, right? Okay. It is going to negative infinity, right? Because this is like monotonically decreasing, right? So if we do f prime x, right? So this is like minus 1 over x. And since x is in the r plus plus, so this is like guaranteed to be like negative, right? Because x is guaranteed to be positive. So this means that this implies that f naught is monotonically decreasing, monotonically like strictly, okay, monotonically decreasing, right? So it will never stop. So it means that this is going to infinity, minus infinity. Okay. Is the optimal value achieved? Like just it's like the previous case, right? It's never achieved. Okay, it's achieved only at infinity. Okay, x going to positive infinity. Okay, is this problem bounded below? So what do you think? Well,
No.
it's no, right? It's evident from P star only. It's evident that's not really bounded below. Okay, so these were like simple. Okay, let us see this case. I mean, these are more or less like not really constraint in the usual sense, I would say. I mean, I can still see this as a constraint because all the time the domain is putting a constraint, right? So in this case, again, x is greater than 0. So that can be treated as a constraint here, right? So, okay. So what is the feasible set? In this case, what is the feasible set? So feasible set is r plus plus again, because these are the allowed values, right? So this is r plus plus. Now what is P star? What is optimal value, right? So from the graph, like we can already see that it takes some optimal value, right? So in this case, not really minus, I mean, it's not going to like minus infinity. So there is something minimum here, right? Now the question is like, what is that, right? So what is P star? So in this case, now like we are supposed to solve this. So to solve this, what do we need, right? So since this is like real valued, we know how to find minima and maxima of this, right? So this is like f naught prime x. So the first step is to find the critical point. So first function into differentiation of the second plus second function into differentiation of the first. So this is like 1 plus log x, right? So to find critical points, f naught prime x is equal to 0. So this implies 1 plus log x is equal to 0. This implies log x is minus 1. This implies x is equal to e to the minus 1, right? So this seems to be, I mean, there is one more step that you have to prove that this is indeed the minima, right? So you do a double derivative test also. So if I do a double derivative, so this will be 1 over x. Okay, so 1 over x is always positive for all x greater than 0. So this implies that x equals to e to the minus 1 must be the minima. So this implies x equals to e to the minus 1 is the minimum, right? And for this, we have to compute the p star, because p star is the function value at x star, right? So this is our x star. So f naught at x star we have to compute, which is, so x star is e to the minus 1 log of e to the minus 1. Okay, so log and e like cancels, right? So log and e will cancel, and this will be like minus of e to the minus 1. So this point itself is like minus e to the minus 1. So you see it's below 0, so it's okay. Okay, so this is what we have solved for this. So p star is like minus e to the minus 1. Optimal value is that. And optimal point is this. Yeah, so this is achieved. And this is x star, which is this. Is this problem bounded below? Okay, obviously, like it's bounded below, right? Because we have found some valid minimum value anyway. So moment you find a p star, valid in the sense like greater than minus infinity, then it's bounded below. And what is the optimum point? So we have found the optimum point, which is e to the minus 1. Okay. So now, so to recap graphically, various scenarios may happen, right? So let us say that this is the constraint we have for our variable. So it should lie in this constraint. Okay, let us say this constraint. So if the function graph is like this, then what do you think, right? So does optimal value, optimal point exist? Okay, so does optimal point exist in this case graphically? Then we see that yes, the optimal point exists, which is here, and this is where the function is taking the minimum value. Remember, our focus is on this interval, right? So this is why we are not looking at these values, which are lower than these values, right? So since we are given only this domain, so x star exists, and this is the x star here, and it is unique, right? Because there is no other x star for which the same minimum is obtained. Okay, there is a local minimum, but this is not x star. X star is the global minimum, right? So x star is only 1. Okay, so this is 1, and in this case, my domain is from minus infinity to up to here. Okay, so does x star exist? Optimal value, optimal point exist or not? Not really. Okay, so because the function is going down and down. Okay, so I have not drawn this. The function is going down and down up to minus infinity. So optimal point doesn't exist, optimal value doesn't exist, and the problem is unbounded below. In this case, if we focus from here to here, then x star exists, but it is not unique, because here it's taking the same values is there, right? So there are 2 points, x1 star and x2 star, for which I get the optimal value. Okay, and in this case, x star does not exist because it's asymptotically going. So it becomes 0 at x equals to infinity. In other words, x star doesn't exist. Okay. Okay. Now there is something called standard form. Okay, because one can write optimization problem in variety of ways, but only when if the optimization problem looks like this, we call that optimization problem in the standard form. And what is to be noted? The point to be noted is on here I always have 0. Okay, here in the equality, I always have 0. Okay, this does not violate our general way to pose the optimization problem, because anything that is not 0 here, you have to move it here and treat whole of that as fi. So this is called the standard form. Okay. In other words, your equality constraint cannot be like this. X star 1 plus x2 square is less than equal to x3. No, this is not correct. You cannot put such inequality constraints in when you talk about standard form. Okay, in standard form, you have to move this guy here. So now it will be x1 square plus x2 square minus x3 is less than equal to 0. Now it is in standard form. Okay, so don't do a mistake that someone gives you an inequality in this form and then you call this, let us say this is the first inequality constraint, and you treat this as f1. Okay, and use some library to solve this, you will be in trouble, because that was not in standard form and library is assuming standard form. So you have to first move this and now you call this f1. Okay, and then you can use library or your own solver or whatever. Okay, so in the standard form, this is the thing to remember. Okay, the right hand side of the inequality and equality constraint are 0 in standard form. Okay, so for example, gi x is equal to, let us say, gi tilde x can be written as hi, where hi is gi minus gi tilde. Okay, I think I forgot to write this. Okay, so I have to redefine hi such that this is this, and then I can write hi equal to 0, and this implies and implied by gi is equal to gi tilde. Okay, so this was the original form that someone gave me as an equality constraint here, and then I redefine h to be like this, and then I get the standard form. Similarly, it may happen that, yeah, so one more thing is there. Okay, there must be always less than equal to in the standard form. Okay, so if you are given an inequality like this, you have to convert that into less than equal to. How will you do that? You multiply by -1 on the both sides. You know that by multiplying by a negative number to an inequality changes the inequality, right? So you have to change this, then it will be minus fix is less than equal to 0, and you redefine this as f tilde ix is less than equal to 0. So now if you are passing this into a library, you have to pass fi tilde. Okay, so these are the things one has to notice. In standard form, you must have less than equal to, you must have zeros here on the right hand side of the inequality or the equality. Okay, there is something called box constraints. Box constraints look like this. So this is my objective function f naught x, and then subject to, and the components of x satisfy this, right? So if I treat x to be in, let us say, R2, okay, and then my function, objective function, is f naught x, and then my box constraint will look like x1 is greater than equal to a, let us say, less than equal to b, and x2 is greater than equal to c, is less than equal to d, right? So this will be, I mean, I have written this two inequalities separately, right? So these are called box constraints. Your components of the x have constraint, and these are box, because if I see R2, let us say this is my a, this is my b, this is my c, and this is my d, then the component of x has a restriction to lie here, and second component of x, which is x2, is lie here, right? So if we look into the domain now, then these are the points, valid points now, that satisfy this inequality, this box constraint. Okay, so since this is like a box, okay, this is like a box, that's why it's called a box constraint. Okay, so there are many problems like this where you have box constraints. So and then this will be higher dimensional box if n is like greater than 2. Okay, so you have a cubic constraint, and then hypercube like constraint, like higher dimensional cube, and so on. Okay, so this, if you see, this is not really in standard form, right? So so what will I do, right? Because what I have claimed before is that I can put things in standard form, right? I can put things in standard form. So in this case, what should I do to put this thing in standard form? Right? So I have to think about this, right? Because here it's like this. So what do you suggest, right? How can I write this in standard form? Right? So can you think about this? So minimize f naught x. Now, how can I write this in standard form so that I have, let us say, I mean, standard form doesn't demand that you must have equality constraint, you must have an equality constraint, but if you have, then this would look like this. That is the demand of the standard form, right? But in this case, I see like there are like inequalities are like this, okay? But what I want are inequalities like this. So what should I do, right? And what is my fi in this case, right? What is fi in this case, and how can I formulate this in standard form, right? First of all, what we know is that these things, so let us focus on the some I, right? Some fixed I, right? So this itself is like two inequalities simultaneously, right? So this is like, so we focus on this thing, right? So Li is less than equal to Xi is less than equal to Ui, right? So this is like Xi is greater than equal to Li and Xi is less than equal to Ui. Okay. So this is nothing but this simultaneous inequality. Now, which one I am allowed to put in the standard form? This is fine because this is less than equal to, but this guy is a very, because this is greater than equal to. So this I will change this to minus, right? So minus Xi is less than equal to minus Li. Now we are still not in standard form. We have to move these guys on the left, right? So this implies minus Xi plus Li is less than equal to 0. And for this guy, this implies Xi minus Ui is less than equal to 0. Okay. So now you see that all these inequalities are now written in this nice form, inequality, and I may have to like redefine things, right? Because this is for I equals to 1 to n, and this is for another set of inequalities from I equals to 1 to n. Okay, so this is like I equals to 1 to n, and this is like another set of inequalities, but I may have to like redefine these variables a bit so that I can start from n plus 1 to n again, right? So it's like 2n. Okay, so I can define something like this where j is how much? N minus I, yeah, n minus I, something like that. Okay. So I will have like 2n inequalities. The first n inequalities satisfy this with hi defined to be like this. And then I have another set of n inequalities for which hj is defined to be like this. Okay. And then I will club them together. And then I will write like minimize f naught x such that h, let us say k now, and k will take care of all I and j combined, right? So hkx is less than equal to 0. Okay, so this becomes in the standard form now. Okay, such that minimize and so on. Okay, so these are the tricks that we have to follow so that any given problem is written in first in the standard form. Okay, so all problem we can do these tricks to write this in standard form. And once we are in standard form, then we can go to the algorithms. Either we have our own solver or the library or whatever. Okay. Okay, so we will do some more practice of putting things in standard form. Okay, so we will do this in the next class. And yes, so for today class, I think we have to stop and yeah, have a nice day. And I will stop now. If you have doubts and questions, then I will be here for a few minutes. Okay.
Sir, here J running